Thank you all for accommodating me on Monday. Hopefully, you've had the chance to both review the notes I posted here and the video on our course YouTube channel, the link to which, oops, wrong button, the link to which is right here. That playlist will take you to every video we've done so far. And here is the recording for Saturday. I'm sorry, for Monday that I did on Saturday, just in case the power went out. And as I said in that video, I like the idea of looking at a table and looking at a graph and understanding what's going on with a limit visually. But I'd rather try and figure these out algebraically. And the algebraic rules by which we do this are called the limit laws. So I'm going to put this in a slightly different order from the book because my opinion is that these first two laws should be, underline that word, should be direct and obvious. I want to think about the limit as x approaches 2 of the function 7. What happens is I'm getting closer and closer to 2. The output of the function f of x equals 7. What happens to the y values? What does the graph of 7 look like? It's a horizontal line, right? So if I'm coming in to 2, and I'm coming from the right, I'm getting closer and closer to x equals 2, what's happening to y values? They're not changing, which means as I come in from the right or as I come in from the left, those y values are staying at 7 no matter what I do, right? So it's irrelevant to me what's going on down here. If I know that y is equal to 7, I'm going to get out 7. As a matter of fact, it doesn't matter what x value I'm going towards. The y values don't change at all. The x is basically irrelevant here. And I'm going to generalize this, and I'm going to say the limit as x approaches a of any constant c is that value c. And really, intuitively, it's because the y values don't change, no matter what I'm doing to the left of a or to the right of a. As I approach a, those y values stay the same. They never move. Does that make sense? Okay. Now let's think about the function y equals x. Even though I don't think of this graphically, I am asking what happens to x as x gets closer and closer to 5. Wait a second. I'm telling you x is getting closer and closer to 5. Now I ask you the question, what's happening to x? Didn't I just tell you that it's getting closer? It's perfect. We know exactly what it's doing. If I tell you that x is getting closer to 5, then the output x is getting closer to 5. If I tell you that x is getting closer to 3, then you have to tell me, well, what's happening to x? Well, x is getting closer to 3. Okay. Again, I'll say it in general. If I tell you that x is going somewhere and then I ask you, where is x going? It's going where I told you. Almost all of the algebraic expressions I am going to deal with are based on the idea of knowing what happens to a number, knowing what happens to an x. Everything else should be constructible from these ideas. And when they aren't, we'll have to go back to our visuals, to our tables, to our graphs to try and figure out what's going on. But algebraically, I'm going to build off of these two. Questions so far? So let's suppose that I have two functions, f of x and g of x. And at some point A, they have limits. In other words, this expression, the limit as x approaches a of f of x, and this expression, limit as x approaches a g of x, both exist and are finite. They're real, regular, ordinary numbers. I don't want to deal with infinities. I don't want to deal with anything weird like that, just numbers. Then, what do you think should happen if I look at the expression made out of adding f of x and g of x and take the limit of that? As we approach that same point A, let's use an example from the pieces we were doing earlier. What if I had the limit as x approaches 2 of x plus 7? I know what happens to 7 as we approach 2. That was the very first example I did today. I know what happens to x as x approaches 2, right? If I'm adding the two functions, what should I do with the two limits? I should add them as well. So really, I'm going to think of this as the limit as x approaches 2 of x and the limit as x approaches 2 of 7 separately. So up here, I'm going to write the limit as x approaches a of f of x and the limit as x approaches a of g of x. The limit of a sum, the limit of a sum is the sum of the limits. My ideas of limits behave the way I want them to. Hey, wait a minute, what's the answer to this thing down here? Exactly. As x gets closer and closer to 2, x gets closer and closer to 2. The 7 doesn't change, so I get 9. If it works for adding, it'll work exactly the same way for subtracting. It will also work that way for multiplying. However, there are two different ways to think of multiplication. This is the more general of the two. If I am multiplying two things together, well, I'm multiplying two things together. The limit of a product is the product of the limits. The limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. The limit of a product is the product of the limits. But if this first function is a constant, then I can really combine two of these. C is a constant. If I think of this as a multiplication just like up here, I should split these apart. So I'll get the limit of C. First rule. The very first rule we wrote down. What is the limit of a constant? If it's a constant, it's C itself. If it's X, it becomes the A. So if I take the limit of the first part, well, that's just the constant itself. And then I still have the limit of the other part. So when I think of multiplying, if I'm just multiplying by a number, I don't need to put the limit on the number. I can just pull it out. This means I can now do simple linear expressions directly. I'm going to be a little bit of a pain in the backside here, and I'm going to write down each and every step, justifying it with the rules we've come up with so far. So the first thing I think of is I think of what happens when I put in a number. What algebraic operations do I do? Well, I do the plug in the number, I'd multiply by the 4, I'd subtract the 5. Let's work the limit laws backwards. The last thing I said I was going to do was subtract. So I'm going to split the subtraction apart. I was going to multiply by the 4. So I'll split the multiplication apart and I'll use this version right here. And now I go back to those first two rules. This is a constant. Limit of a constant is the constant itself. This is the limit of x. Here, the limit of x is whatever I have down here. As x gets closer and closer to 3, x is going to give me a 3. And so I end up with a number. If you were to graph this expression, you would see a line. And you could do exactly what we did in Monday's discussion about drawing on the graph and approaching from either side. But here, algebraically, I don't need the picture. Questions? Yes, sir.
So I know we did it in like every step, but are we like able to put like plug in the X?
That is what that looks like, right? If I just took that 3 and I plugged it in right here, that's what I got down here. That works sometimes. Table flip. How do I know when? I'll get there. And once I know when, then yes, I can absolutely just go ahead and plug in. But I need to know when that works and when it doesn't. Unfortunately, I'm not there yet. More questions? At the top of the screen, I'm multiplying. There's a shorthand for multiplying by the same thing, right? So if I think of this, x squared, but x squared is just x times x. And if I'm multiplying, I use that rule up there and I split them up. But I just said that when I'm multiplying the same thing by itself, that's the definition of being squared. Isn't the thing in this set of parentheses the same as the thing in this set of parentheses? That's the same thing. So why don't I just write it as the limit squared? Oh, a power, x squared is on the inside of my limit. It ends up on the outside of my limit. What if I had x cubed? Because I would take the x and the x squared, spread them apart, the x squared would jump to the outside, I'd have one more, it would be 3 of the same thing, I'd write it as cubed. This works for any power. Now here's the best part. It works for any power. That means it works for weird powers too. Cast your mind back to algebra class. What power goes with a square root? A 1/2 power. And if I rewrite this as a 1/2 power, I can play this trick right here. And I can say, oh, really? And a 1/2 power is a square root. I can do that. And the same game can be played no matter what root I have. I don't care if I've got a square root or a cube root or a 17th root or a 2/3 root. I can do it for any power I want. As long as I rewrite that root as a power, this change works. Provided, what can't you use in a square root? I can't have a negative number in a square root. So I've written the limit as x approaches 9 of x under that square root. That means that the thing under the square root is positive. I can take its square root. If I try and take the square root of a negative number, my calculator gives me something with an I in it. Imaginary numbers are wonderful, beautiful. I love them dearly. They are not appropriate for this course. We'll leave them somewhere else. If you're interested in talking about square roots of negatives and what imaginary numbers do, I did my research work in imaginary numbers. I am more than willing to talk your ear off about it. I got some really cool pictures that go with that, but that's not this course. So I have to be careful when I'm looking at roots that the root I am using makes sense. You can't have a negative in a square root. You can't have a negative in any even root. Odd roots, perfectly fine. The cube root of -8 makes perfect sense. The square root of -8, but I just have to be careful of the order of my root. Questions? Adding, subtracting, multiplying powers and roots are parts of multiplying, dividing. What should the right half of this be? What's the appropriate expression on the right half of this set? If I have f of x over g of x, is there a way I could think of that as multiplying? Chase, you're nodding at me, talk to me. How do I make it multiplying?
We could, like, we're gonna keep the,
So I could write it as f of x times 1 over g of x. And then multiplying says just split them up, right? And then the limit for the g of x, does the top ever change if it's always a 1? Only the bottom will change. If only the bottom will change, I could actually do that right here as one step. And I could say, really, I'm going to take the limit of the top and the limit of the bottom separately from each other. So if I think of that 1 over g, well, then I take the limit of the g part, the 1 wouldn't change, so the limit will end up on the bottom instead of staying out in front on the top. Again, I have a question. Where does this get up? Where does this blow itself up? There's a physics joke in here too. What are you not allowed to divide by? A physics joke. Black holes are where God decided to divide by 0. So as long as I'm not dividing by 0, this is fine. If I'm dividing by 0, then I have a problem. There was one specialty that we've already looked at where dividing by 0 was okay and worked out. Both Monday and Friday last. What division by 0 worked? Even gave it a name. Zion? I'm sorry? NPQ. When I had a 0 divided by 0, I gave it the name indeterminate form. As a matter of fact, this was the example I had in Friday's notes, because if I just put in 1, I got 0 over 0. So I'm dividing by 0, but because it's a 0 on top, that one actually worked. So there are cases where this can work out. But it's not truly just dividing by 0, it's an indeterminate form. We'll figure out more on what to do with those as we go on. Okay. Chase, I'm about to make you happy. If I have a polynomial or a rational function with x equals a, an element of the domain of, I got to go back to my algebra class. What the hell do all these words mean? What's a polynomial?
One, it's like, there's no power there, it's one, like a one-way function.
Well, one way, my hope is that all of my functions are one way. But they go from and to, and there's only one output for each input. That's the definition of a function from algebra class. But what makes something a polynomial? Wait a minute, what's poly mean? Multiple. Known. Nomenclature. All of you sciencey chemistry people. Nomenclature means names of things. We name things. Biology, nomenclature, all of those, kingdom, phylum, all that garbage. Nomenclature. Polynomial means many named pieces. So a polynomial is something that has numbers and powers of x. Now those a's are all numbered. So like 7x to the third plus 2x to the fifth, squared. I'm writing them in descending order of power. So the highest power on the left, and I work my way down as I go from left to right. So x squared plus 2x minus 7 is a polynomial whose highest power was 2. X cubed minus 13x plus 4 is the highest power 3. That's a polynomial. Multiplying, adding, subtracting, whole number powers for x. That's a polynomial. Rational. What's rational? In a math term, not a psychology term. Because trust me, I'm irrational. Fractions. And in particular, a rational function is a polynomial on top and a polynomial on the bottom. So a rational is made up of a fraction of those things, a ratio. And having the number be part of the domain means that when I plug in the number, I get an answer out. I don't get something that's undefined. I don't get something that's dividing by 0, especially in a fraction like that, right? I want to make sure the bottom works. If both of these conditions are true, or I have a polynomial, then I just plug in. So I can say, I want to plug that in. All I have to do to find this limit, instead of breaking it all up and using all those rules, is to simply put the 2 in there. That's it. Plug and chug, works perfectly. Polynomials are defined everywhere. You can put any value of x into a polynomial. In a rational function, you can only put in the numbers that don't make the bottom zero. If I go to plug in, what happens? Damn. But wait, there's more. Something really sneaky happens when I plug in on top. That makes this not an impossible. That makes this one of my indeterminate forms. That makes this something I might be able to fix. So now the question is, what the hell do you mean I can fix this? Do me a favor. Graph this. Graph this expression, x squared minus 4 over x minus 2. What do you see? What's your graph look like? Except if you hit trace and you put in 2, you get y equals blank, right? So it's really a straight line with a hole in it. When I graph this, I get this. By the way, if you're not getting this, please make sure that you have put parentheses around the x squared minus 4 and parentheses around the x minus 2 in your y equals line. The most common mistake when dividing a rational function like this is to forget those parentheses. I'm taking the limit as x approaches 2, yes? Based on what I said the other day on Friday and Monday, that means I don't actually want to look at what's going on at 2. I want to look at what happens as we get closer and closer from the left, and as we get closer and closer from the right. Isn't this function behaving perfectly nicely there? So when I look right at 2, I see something weird. But a limit doesn't want me to look at 2, it wants me to look as I approach 2. I feel like I'm in the Wizard of Oz. Pay no attention to the spot behind the curtain, just pay attention to what's going on around it. And if I can figure out what's going on around it nicely, then I can get a limit. So let's consider if I could find some other function that looked the same as this one everywhere else. You said it was a straight line. Do we happen to know the equation of this line? Is there an algebraic way we could figure out the equation of this line? I could go through and find points and do the slope idea, or I could take this and start doing algebra on that. I look at the top of this expression and I see x squared, I see 4, and 4 is a square, isn't it? What is the square root of 4? And that makes that expression on top the difference of two squares. I reach back into my memory banks, grab my algebra class, pull it back to the forefront, and say there was a pattern about dealing with the difference of two squares, about factoring that expression. Fiona, what is that expression's factorization? Aha. And if I were to write this in this fashion, I could think to myself, well, maybe I can cancel the x minus 2's, right? So let's do that. And my resulting expression is just x plus 2. By the way, if you go back into your calculator and you graph y equals x plus 2, you'll get exactly the same line and you'll fill in the hole. Now, you'll notice I did not write an equal sign. This is me being a pain in the ass. Because technically, this expression is not defined when x equals 2, but this one is. So they're really not the same. They're the same everywhere except at 2. And that's the important part. They're only different at this spot. I'm going to put an asterisk there. I promise I'll come back and explain what that asterisk is in a moment. And what this tells me is that if I have a function and there's a problem at one spot and I can find another function that's the same everywhere else, then I can swap them out. And instead of doing the limit of x squared minus 4 over x minus 2, I use the limit of x plus 2. And that means that I can actually compute this directly. And that thing on the left was 0 over 0, but the thing on the right isn't. It's a polynomial, which means I can just plug in. So I can fix indeterminate forms if I can do algebra to make them no longer indeterminate. If I can determine them, indeterminate becomes determined. Questions? Yes, sir.
This only works for polynomial and exponential function ones.
Correct. Now, that's not only the case provided that when I do the determining, I make it polynomial or rational. So here's a crazy one from Monday. Now, when we did this in Monday's lecture on videotape, I said my problem is my calculator is going H. And when t is really small and I square it, I get 9.00000001. When I take the square root of that, it loses the 1 because it only has a finite amount of precision for each number in my calculator. So it thinks this is 0 divided by something that's not 0. But when I look at it from a bigger picture, it looks like it's going to 1/6. I didn't pull 1/6 out of thin air. I want to do some algebra because this is 0 over 0 if I just go to plug in. It's indeterminate. So unfortunately, Chase, this is not a rational expression because that's square root. And I can't keep doing the same ideas by factoring. What I could do is unfactor. I'm going to multiply. I'm going to multiply by 1. The only thing I can multiply by that isn't going to change stuff is 1. But I'm going to write 1 weird. Fiona, you said it was x minus 2x plus 2, right? Think of this as thing minus 3. I'm going to multiply by thing plus 3. That'll be like it's set up for my difference of two squares, isn't it? A plus b, a minus b. I'll have the two correct pieces. So the thing I'm going to multiply by is 1. It's just a gross as hell looking 1. Okay. I'm not even going to do anything with the bottom. I'm just going to leave it written just like that. But on top, what happens when I multiply these two expressions together? I'm going to distribute. So I have the square root times the square root. What happens? Thing times itself. It cancels out the root. I get this thing squared. Well, that means the square root goes away. Then I get minus 3 times the square root and, this one tight, 3 times the square root from the outside. I got a minus 3 square root and I got a plus 3 square root. What happens? Then I have minus 3 times 3. -9. Hey, wait a minute. Look at what just is about to happen on top. On top, I'm going to get t squared plus 9 minus 9. Plus 9 minus 9, what happens to those? So that makes the top just a t squared. And don't I happen to have t squared times stuff on the bottom? Notice it's even outside a set of parentheses. And that means it's being multiplied. That means I have to cancel that t squared on top and bottom. Now this expression is rational, except for that square root on the bottom. So let's do our division idea. If I take the top, I'm just going to get the limit of 1. The top's going to stay 1. On the bottom, I'm going to get a square root. I can bring the limit from outside the square root to inside the square root. Then the thing I'm taking the limit of is a polynomial, t squared plus 9. What happens when you plug in 0 for t squared plus 9? Square root of 9 is 3. Hey, wait a minute. That gives me 1 over the square root of 9 plus, that's 1 over 3 plus 3. That is 1/6. Son of a... It worked, master. It worked. My algebraic behavior, as long as I can find the right way to do the algebra, is going to save my bacon. It's going to make my life a lot easier. Please note, some of our limits will still give us a problem because some of our functions algebraically are defined weird. Questions? What do those vertical bars mean? And the absolute value makes numbers do what? So anything that's negative becomes positive. really, this is defined in two pieces. It's defined on the left side of 0 as multiplying by -1, because you take all the negative numbers to make them positive, you got to multiply by an extra minus sign. But for numbers that are already positive, you don't do squat. So I want to think of this really as this function being defined in two pieces. There's a lovely visual for this. If I graph the function the square root of x, I'm graphing a line on this side with slope 1. I'm graphing a line on this side with slope -1. So, if I think of this limit, what do I get? As x gets closer and closer to 0. I get 0. No matter which side I'm coming in from, I'm getting closer and closer to 0. Beautiful, wonderful, marvelous. Now I'm going to use this to mess with me. I could try and graph this. You have an absolute value function on your calculator. You absolutely could graph this. But I'm going to split this up because this behaves differently to the left side of 0 and the right side of 0. And this is an indeterminate form. If I go to plug in, I get 0 over 0. I don't know what to do with that. So let's do a left side limit and a right side limit separate from one another. Okay. That little minus sign means I am approaching only using numbers that are to the left, the negative side of 0. That means I'm in this part of my function. So I'm going to replace this absolute value with this expression. That's an indeterminate form. But algebraically, what is that equivalent to? Simplify this. That's a constant. Do I care where you're going when you have a constant? So this is just going to give me -1. So the limit from the left is negative. What happens when I do this from the right? Well, I'm going to play the same game and I'm going to replace the absolute value with the appropriate part. I'm only using positive numbers this time. What algebra simplification happens here? It's +1. So what is the limit that we originally were looking at here? What do I get for this answer? From the left, it's negative. From the right, it's positive. In order for the overall limit to exist, those two values have to both exist and they have to be the same. So this limit up here does not exist. Because those don't match, that was enough. It is to my benefit to be able to look at functions compared to one another. I unfortunately have literally 0 minutes left, so I'm going to do the last two theorems. They're very general. tomorrow before I start taking questions. So tomorrow is question and answer day. On Friday, chapter 2, sections 1, 2, and 3, homeworks are due. You should bring questions tomorrow. You should have looked at all 3 of those, but know that I will be doing those last 2 theorems at the end of chapter 2, section 3, at the beginning of class tomorrow. I will see you all then. Have a wonderful rest of your day.